330 light-years from Earth, a planet moves through darkness in its own thick envelope of atmosphere. The James Webb Space Telescope just looked into that envelope. It read the chemistry there, and it found methane, a molecule that contradicts what we thought we knew about how giant planets hold onto their gases. TOI-99b is Saturn-sized, a giant world made of gas and ice. Nothing like Earth, nothing with a solid surface. It orbits a yellow dwarf star, a star much like our Sun, but younger. The orbit is close, extremely close. TOI-199b circles that star once every 100 to 105 days. For context, Mercury, the nearest planet to our Sun, takes 88 days. TOI-199b is comparable. That proximity floods the planet with heat. Sunlight hammers it constantly. The dayside temperature reaches approximately 175 degrees Fahrenheit, about 79 degrees Celsius. Hot enough to boil water, not hot enough to melt rock, not cold enough to freeze ice. It sits in a middle zone that astronomers call temperate. A giant planet in a temperate orbit is rare. Most massive planets either huddle close to their stars in furnace heat or drift far away in frozen darkness. TOI-199b occupies the unusual middle ground. The planet was discovered years ago and catalogued as one of thousands of known exoplanets. Cataloging and understanding are not the same. Understanding requires looking deeper. It requires analyzing light. Transmission spectroscopy is the method. Here is how it works. Every transit, when a planet passes in front of its star, some starlight reaches Earth by filtering through the planet's atmosphere. Different molecules absorb different colors of light. Methane absorbs certain infrared wavelengths, so do ammonia and carbon dioxide. Each molecule leaves a signature. The starlight that reaches Earth is dimmed at those specific colors. A sensitive spectrograph can measure this dimming. It can identify which molecules created the effect. Webb carries the near-infrared spectrograph, called NIR-SPEC. It was built to catch exactly these faint infrared signatures. NIR-SPEC watched as TOI-199b transited. During that brief window, lasting a few hours, the instrument gathered photons from the star, photons that had passed through TOI-199b's air. The data revealed methane, clear methane, traces of ammonia, carbon dioxide as well. For the first time, astronomers had a detailed read on the composition of a temperate giant's atmosphere. This is unprecedented. Astronomers have measured hot Jupiters, massive planets in extremely close orbits, baked to temperatures above 1,000 degrees. We have detected atmospheres around some distant ice giants, frozen worlds far from their stars, but no one had successfully characterized the atmosphere of a temperate giant. The signal is fainter. The atmospheric layers are thinner. The fingerprints molecules leave on starlight are subtle. Webb's infrared power finally made the measurement possible. TOI-199b is the first. But methane should not be there. That is the problem. Methane is unstable. Ultraviolet light from the star breaks methane molecules apart. The carbon and hydrogen scatter. Over millions of years, a planet in a close orbit should lose nearly all of its methane. The models that predict planetary atmospheres all assume this. If a planet is close to its star and receives strong ultraviolet radiation, it sheds volatile compounds. If a planet is distant, it may never have accumulated much methane. TOI-199b is close. It receives plenty of ultraviolet. By all expectations, it should have already lost its methane. Yet methane is there. Webb detected it. The Astronomical Journal published the findings in May 2026. The data is unambiguous. TOI-199b presents a genuine puzzle. Why would methane persist on a temperate giant? Several explanations exist. First, the planet might be younger than current estimates suggest. Younger planets have not had sufficient time to lose their primordial gases. The calculations that determine a planet's age rely on models of stellar evolution. If those models are slightly off, age estimates drift too. A planet that is actually younger might still hold on to its original methane. Second, chemistry might produce new methane. On Earth, methane comes from life, swamps, bacteria, cattle. Life does not exist on TOI-199b, but reactions might. Reactions in the atmosphere or between the atmosphere and the planet's interior could generate and release methane. Geochemical processes, not biological ones. If such reactions occur, they could replenish methane that ultraviolet light destroys. Third, collisions might explain it. Comets and asteroids carry methane compounds and methane ices. If TOI-199b was struck by such bodies recently, a few million years is recent on planetary timescales, the impacts could have injected methane into the atmosphere. A newly enriched air would take millions of years to lose that methane again. Fourth, we might misunderstand the loss mechanism itself. Perhaps methane clings to giant planets longer than chemical models predict. Perhaps ultraviolet light at TOI 199b's star is weaker than we think. Perhaps methane condenses and rains back down, cycling rather than escaping. Perhaps atmospheric processes we have not accounted for slow its escape. None of these answers are certain. The discovery does not solve the puzzle. It reveals that the puzzle exists, and revealing puzzles is often what science does best. The implications extend beyond TOI 199b. Planetary atmospheres are records. They contain fingerprints of history. When a planet formed, what it accreted, how its star treated it, what collisions shaped it. If our models are incomplete, our ability to read these records is compromised. Every atmosphere we measure becomes harder to interpret. Every conclusion about a planet's past becomes less reliable. Webb is young, only a few years in orbit, but already transformative. More temperate giants will be observed. Their atmospheres will be analyzed. Some might contain methane, others might not. Over time, patterns will emerge. If methane is common, the models need fundamental revision. If it is rare, TOA 199b is an outlier, unusual, worth further study to understand what makes it different. The light from TOI 199b's star continues to travel toward Earth. In months, the planet will transit again. Webb might observe once more. Over years and decades, data will accumulate. The puzzle will deepen. For now, 330 light-years away, a methane-rich temperate giant waits in its own atmosphere.